Hey everyone, and welcome back. Today we're doing a deep dive into deep learning with this book, Dive into Deep Learning. We've got excerpts prepped and ready, and it looks like you're all set to go beyond just those code snippets.
For sure. You know how sometimes you'll see online tutorials and it's just code, code, code?
Definitely.
Yeah, well, this book really wants to make sure that you get the why behind the what in deep learning.
I like that. It's like someone tried to bake a cake, but all they have is the ingredient list. You might get something, but who knows if it's what you wanted. Now, I noticed that they decided to use MXNet in this book. Was there any particular reason for that?
So MXNet, it's kind of like the best of both worlds. It gives you the flexibility that researchers need when they're experimenting, but it's also powerful enough to actually use in building those real-world applications. And what's cool is this book uses both raw NumPy and then that higher-level gluon code.
Okay.
So you get to peek under the hood and you learn how to use it practically.
So it's theory and the practical tools all in one. I like that. What are some of the big things that we can expect to really dive into and learn about here?
So after they lay some groundwork, the book really jumps into some really interesting stuff. First up is convolutional neural networks.
Ooh.
CNNs. These are like the heavy hitters for image recognition.
Right.
After that, they cover recurrent neural networks, RNNs, and those are perfect for language processing because they can work with those sequences of data.
Oh, and speaking of language processing, they even get into attention mechanisms, which seems to be the hot new thing. Well, not so new anymore, but still very cool.
Oh, for sure. If you think about how we as humans, when someone's talking, we're focusing on certain words to really understand the meaning, that's basically what attention mechanisms are letting AI do.
That's amazing.
Yeah.
But before we get too far ahead of ourselves, how does this book approach actually setting up and sort of diving in on the practical side?
And they don't waste any time. The book walks you through getting that dedicated environment set up. It's called D2LMN and installing MXNet. And it even reminds you, hey, make sure you've got the right GPUs because this stuff can get pretty demanding on your computer.
Yeah, it's like having a powerful enough oven to bake the giant multi-tiered cake, right?
Yeah.
That's a good analogy. I really loved that aha moment the book opens with about recognizing the word Alexa. It's really incredible when you think about the power of machine learning.
Such a good example. Because think about it, you can probably tell when someone is saying Alexa, even if you don't know anything about programming or how that works.
Yeah, for sure.
And so deep learning's tapping into that human ability by taking tons and tons of that labeled data, audio clips that are labeled Alexa, not Alexa, and then it can train a model to kind of spot those patterns.
Without us having to spell out all the rules.
Yeah.
It can figure it out on its own. But I do have a question. What exactly are these models that we always hear about in deep learning?
Models are like the chefs in the deep learning world. So they're taking in all that raw data, like ingredients, and then they use this set of instructions to process it all and spit out a prediction that's like your finished dish.
Okay.
And deep learning models are kind of special because they have so many layers of processing.
So more layers, the more deep and complex they are.
Exactly. It's like adding all those extra steps to your recipe to really get that rich flavor. Each layer is learning all those really intricate representations of the data.
Okay, that makes a lot of sense. But how do these models actually learn? It all seems very, I don't know, magical.
So that's where optimization algorithms come in, and specifically something called gradient descent. Imagine you're trying to find the bottom of a valley, but it's pitch black. So at each step, you're kind of feeling around, seeing which way is sloping downwards. Take a little step in that direction. If you keep doing that, you're going to eventually hit that lowest point. Gradient descent is kind of like that, but for models, it's guiding them to the very best parameters so they can make those accurate predictions.
So it's systematically feeling its way towards the best solution.
Exactly. Now, another really key concept is how the data is actually represented. Computers, they don't see images like we do.
Right.
They see grids of pixel values, which get translated into these things called tensors. They're multidimensional arrays.
Tensors. I've heard that word thrown around, but I'll be honest, it's always sounded a little intimidating.
Think of a tensor like a spreadsheet, but on steroids.
Okay.
So just like you have those rows and columns, tensors can have a whole bunch of dimensions. And just like you can add or multiply cells in your spreadsheet, there's this whole world of math that you can do with tensors. That's tensor arithmetic.
Okay, so we're teaching computers to see images or understand them in their language.
Exactly. And the book actually does go into some of the math behind it, like
Yeah.
summation over tensor elements, matrix multiplication.
Right.
But it also emphasizes that it's really important to visualize your data.
A picture's worth 1,000 equations, or however that saying goes, right?
Exactly. Seeing the data and what your model's actually predicting visually can really help you grasp what's going on.
For sure.
And the book actually introduces a custom plot function that you can use to create those really nice, clear, and concise graphs.
That's really cool. Having those visuals can make things so much easier, especially when you're dealing with all this math. It can be very daunting.
Yeah.
Speaking of which, the book mentions this thing called automatic differentiation, which sounds like it could be a lifesaver.
Oh, it definitely is, especially if calculus isn't really your thing.
Right.
So calculating these things called gradients, which are kind of like slopes, but in a multidimensional space, that's super important for optimization. But MXNet has this really cool package. It's called AutoGrad.
Okay.
And it basically does all that heavy lifting for you. So you define your computation, and then it figures out how to compute all those gradients automatically.
So no more manual calculus. That's a win.
Exactly.
I notice also that the book dives into probability. How important is probability when we're talking about deep learning?
Probability is actually the foundation of machine learning.
Okay.
It helps us make sense of all the uncertainty that's in data and then allows us to make predictions from it. So the book covers stuff like probability theory, random variables, and all these different kinds of distributions like the Bernoulli and Gaussian distributions.
Oh, yeah. Vaguely remember those from stats class.
Well, they're back in a big way in deep learning because it's how we can actually model and analyze all the data that we're feeding these models.
Right. So we've got our data represented, but what are we actually doing with all of this? What are some practical applications?
One very common application is linear regression. You know how Zillow tries to guess what your house is worth?
Right.
That's linear regression in action.
Okay.
It's taking things like the size of your house, location, number of bedrooms to predict that value.
So it's assuming a linear relationship between those features and the price.
Exactly. And while that works really well for some things, the book actually highlights how those more simple models, they often fail when things get more complex. That's where deep learning comes in.
Okay.
But we'll get into that more a little bit later. For now, another really important task is classification. So this is teaching a computer to categorize things.
So instead of giving you a number, it's telling you if it's a cat or a chicken.
Exactly. And this is where things like softmax regression come in.
Okay.
So that takes all those raw scores and then transforms them into probabilities. So it's telling you how likely is it that this image is a cat, a chicken, or something else entirely.
Okay, so we're categorizing, we're predicting values. Sounds like we're building some pretty smart systems here. But there was also just this quick mention of information theory. What role does that play in all of this?
Information theory is a super fascinating field. It gets into how to actually quantify information.
Okay.
And it measures things like entropy, which is basically just a fancy way of saying randomness or uncertainty. And it also covers something called Kullback-Leibler divergence, which is measuring how different two probability distributions are from each other.
So it's really about understanding and quantifying the information itself.
You got it. And while this book only gives us a little taste of information theory, it's definitely something we could do a deep dive on another day.
Noted. We'll add that to the list.
For sure.
Now, going back to the linear models, you mentioned they have their limitations. Can you elaborate on that a little?
Sure. So think about this classic example. Classifying cats versus dogs. Linear models, they really struggle with that because they're relying on those simple relationships between individual features.
Okay.
But with images, it's not just about those individual pixel values. It's how all those pixels work together. It's the complex interactions and patterns that make a cat or a dog. And linear models, they just aren't expressive enough to capture all of that.
So how do we go beyond those limitations? Is that where these deep networks come in?
Exactly. Deep networks with all of their layers can actually learn those complex patterns that the linear models, they just miss. Think about it like this. A linear model, it's trying to understand a painting by looking at each brushstroke individually. But a deep network, it can see the whole thing. It gets how all those brushstrokes are working together to make the masterpiece.
That's a great way to put it. So these deep networks are really looking for the bigger picture.
Exactly. And in order to do that, they need to introduce this non-linearity.
Non-linearity. That sounds complicated.
It's actually not as scary as it sounds. Remember those activation functions that we were talking about earlier?
Right.
Those are key for this.
So they're adding those twists and turns to the way that the model makes decisions.
Exactly. The book talks about sigmoid and ton activation functions. And they're basically introducing these smooth, nonlinear transformations that let the network learn these way more complex relationships.
Okay, so we're adding layers, we're introducing this nonlinearity. Sounds like we're building some pretty powerful models here. But I've also heard that you have to be careful not to make them too complex. Something about overfitting.
Yeah, that's a really good point. It's kind of like Goldilocks and the porridge, right? You don't want it too hot or too cold. You want it just right.
Right.
Same with models. If a model's too simple, it can't really grasp the data, and that's underfitting.
If it's too complex.
Then it ends up memorizing the training data, but then it can't generalize to anything new that it hasn't seen before, and that's overfitting.
So what's the solution there? How do you find that just right model?
So one really powerful technique is called dropout.
Dropout. They're dropping out of school?
Not quite. Imagine a team, right, where different members have to step up and cover for each other when someone's out. That actually makes the whole team stronger overall.
Okay.
Dropout is doing that, but for the model. So during training, it randomly drops out different neurons, which forces the other ones to pick up the slack and learn more well-rounded representations. And it keeps the model from relying too heavily on any one neuron.
So it's building a team of more well-rounded players instead of relying on that one star player.
Exactly. And, the book actually gets real about a common problem in deep learning. Like the real world, it's messy.
Right.
So training data is often really idealized, but when you actually use your model out in the wild, it's going to see data that's different than what it was trained on.
Different how?
So the book talks about a covariate shift, label shift, concept shift. It's basically just all the different ways that what you trained your model on might not actually match what it's seeing once it's, out in the real world.
So then how do you deal with that?
That's where things get really interesting. You have to make those models more robust. It's a whole other deep dive in itself, though.
Noted. We'll add that to the list.
Yeah.
So let's say we've built our model. How do we actually know if it's any good? How do you choose the best one?
So that's where model selection and cross-validation come in.
Yeah.
Imagine you're trying to find the very best route to get to work. You're not just going to use one map, right? You might look at a few different routes, see which one consistently gets you there the fastest. That's what cross-validation is doing. Techniques like k-fold cross-validation, they're basically splitting your data, and then they use some to train and some to test. So it's like your model is testing those different maps.
So it's really testing its ability to navigate new territory.
Exactly. And through that, you can choose the very best model, the very best hyperparameters. Those are like the settings that control how the model learns.
Okay, that makes sense. So we've got this model selection down. But actually building these models still seems kind of daunting. Are there ways to make it a bit more manageable?
Oh, totally. So the book talks about layers and blocks, and they're like Legos, but for deep learning.
Lego. So we're building with pre-made components now.
Exactly. Layers, those are the basic building blocks. And then blocks are these groups of layers, and they work together to do something specific. The book actually talks about blocks in MXNet as reusable components.
Okay.
And they make designing and building these models so much easier.
That's a relief. So it's not all coding from scratch.
No, not at all. Deep learning is all about using what others have already done. And speaking of building, the book also really emphasizes how important parameter initialization is.
Parameter initialization. Isn't that just like choosing a starting point for the model?
It is, but it's way more important than you might think. Think about launching a rocket into space.
Okay.
If you have even a tiny miscalculation at the very beginning, it could end up miles off course.
Right, so that starting point really matters.
Huge. And the book shows you how to actually customize these initialization strategies to give your model that good starting point, help it get to a good solution.
So we've got the building blocks, we're initializing them correctly, but what about the hardware? We touched on GPUs a little bit, but how important are they really?
They are so crucial, especially when you're talking about deep learning. Remember that giant multi-tiered cake analogy?
Right.
GPUs are like having a professional-grade oven. And not just that, one with a ton of racks.
Okay.
So they can process so much data at the same time. That makes the training go way faster.
So no more waiting hours, maybe even days for your model to train.
Exactly. And the book shows you exactly how to take advantage of that using MXNet.
Amazing. Now, I'm excited to actually dig into some specific architectures. We touched on CNNs earlier.
Yeah.
Those ones for image data, right?
That's right. CNNs, they're designed to work with how images are laid out. It's that spatial structure, and it's actually a lot like how our own eyes process information.
Oh, so they're mimicking the human eye.
In a way, yeah. They use these things called convolutional layers. It's kind of like a sliding window. It's scanning across the image, and it's pulling out those features. And then the book gets into some other cool stuff, translation invariance, which basically means that the network can figure out the object no matter where it is in the picture.
Yeah.
And it also talks about strides, padding, and pooling.
Okay.
They sound complicated, but they're all just ways to control how big and complex that network gets.
So it's kind of about extracting the essence of an image.
Exactly, no matter the size, no matter the position.
Mm.
And these techniques, they've led to huge progress in image recognition. In fact, the book actually goes into some of the pioneers in this area.
Like who?
Well, there's Lynette, which was one of the first really successful CNNs. And it was so important because it showed how powerful convolutional layers are. And then there's AlexNet, which that one really shook things up in the deep learning world.
What made AlexNet so special?
Well, the architecture, for one thing, it used these things called ReLU activation functions.
Okay.
They're really efficient for computers, and they help with this thing called the vanishing gradient problem.
The vanishing gradient problem. What's that?
Yeah, so that's when the gradients that are used to update the model, they get really, really small as they go back through the layers, and then that makes it hard for the model to actually learn.
Okay.
And then ReLU swoops in and saves the day because it doesn't squash the gradients as much.
Gotcha. So it's like it's clearing the path for those signals to get through.
Exactly. AlexNet also used dropout, remember we talked about that earlier, to prevent overfitting.
Right.
So really a combination of clever design and these cool techniques. And its success on this data set called ImageNet, which is massive. It has tons of labeled images that really show just how powerful deep CNNs could be.
It's really incredible how far things have come.
Yeah.
Are there any other really important techniques when it comes to training these deep networks?
Definitely. Training really deep networks, it can be tricky. It's like trying to build this tall tower, but it's out of blocks. It could get wobbly.
Right. So how do you keep it from tipping over?
That is where batch normalization comes in. It makes training smoother, improves performance by normalizing activations, and it does that in each layer.
Normalizing. What does that mean exactly?
It's like making sure that all the data is flowing through the network in a nice, organized way. Think about a conveyor belt. It's moving packages, and they're all different sizes. Batch normalization is like this system that adjusts the speed, the spacing to make sure everything moves smoothly and efficiently.
So it keeps everything running smoothly.
Exactly.
Batch normalization, CNNs, AlexNet. My brain is buzzing with all of these breakthroughs.
Right. It's amazing how far things have come. But, like with any field that's rapidly changing, even the experts are still trying to figure some things out.
Are they questioning assumptions, going deeper on stuff?
Exactly. Like the book, it actually mentions how that initial explanation for why batch normalization works so well, this thing called reducing internal covariate shift, it might not be the whole story.
Internal covariate shift? That's a mouthful.
Yeah. It basically means that, the way those activations are distributed, it can change during training, which can really mess things up.
Okay.
But it's not quite the same as that covariate shift we were talking about before, with the real world data and all of that. So batch normalization, super powerful, but we're still trying to figure out exactly why.
That's a good reminder that this is a field that is constantly evolving. It's not like we have it all figured out.
Exactly. And that's part of what makes it so cool. There's always something new to discover.
Right.
Speaking of, the book then goes on to another type of neural network. This one's called recurrent neural networks, RNNs.
RNNs, and those are the ones that are really good at understanding things like language where the order of the words really matters, right?
You got it. Natural language, time series data, anything where the order is key.
Okay.
And what's so cool about RNNs is they can actually use information from the past to influence what they're outputting now.
So they have a memory, kind of?
Yeah, you could say that.
Yeah.
Keep this thing called a hidden state. And it's like their short-term memory bank. It stores those little bits of information from the past.
That's wild. It's like the computer program actually remembers what it saw before. And there are different types of RNNs, right?
You're right, there are. The book goes into those basic RNNs and then some fancier versions, LSTMs and GRUs.
I have to admit, those acronyms, they're a little intimidating.
They can be a mouthful, but they're really just clever ways to make those RNNs even more powerful.
Okay.
So LSTMs, that's long short-term memory, and GRUs are gated recurrent units.
Okay.
And these guys, they're here to tackle that vanishing gradient problem.
Right, we talked about that.
Exactly. They have special ways built in that let them learn those long-range dependencies, when things are far apart in the sequence.
Okay.
They're like the memory champions of the RNN world.
Which is really important for understanding language, right?
Yeah.
Because one sentence could refer to something from, like, paragraphs ago.
Exactly. And when you're talking natural language processing, the way you prep that data is super important. The book uses an example of building a language model. So that's basically a model that's trying to figure out what the next word in a sentence is.
I've seen those. You type in a few words and it tries to guess what you're going to say.
Exactly. But before that model can even try to do that, you have to process all of the text.
Okay.
So the book talks about tokenization. That's breaking it down into those individual words, subwords, and then you build a vocabulary, which is like a dictionary for the model.
So you're teaching it the language before you can actually speak it.
Exactly. And in that whole process, they introduced this really fascinating concept called Zipf's law.
Zipf's law? What's that about?
Oh, wait. So it's this really cool thing about how language works. Basically, it says that, like, how often a word shows up, it's inversely proportional to its rank in the frequency table.
Oh.
So, like, in simpler terms, the most common word in a language, you're going to see that, like, twice as often as the second most common word, 3 times as often as the third, and so on.
Huh. I didn't realize there was, like, an actual pattern to it.
Yeah, it's a super cool pattern, and it actually holds true across a lot of different languages, and it has real implications for deep learning, especially for a technique called subsampling.
Subsampling, is that like reducing the amount of data?
Not exactly reducing it, but more like balancing it out. So words like the, a, they show up all the time, right? And they can kind of drown out the more important words that don't show up as much. Subsampling helps to, like, downweight those really, really frequent words so the model can focus on learning more about the nuances of the language.
So it's filtering out the noise so it can hear the important stuff.
Exactly. Now, the book, it gets into how RNNs work, all the equations, forward, backward propagation through time.
Yeah, probably don't want to bore everyone with all the mathy details.
Right.
But just to clarify, that back propagation through time, that's how the model actually learns from those mistakes over, like, a whole bunch of inputs.
Exactly. It's basically like back propagation, like in a regular network. But instead of going back through the layers, it's going back through those different points in time.
Okay, so it's like training a regular network, but with a time machine built in.
Exactly. Now, another interesting thing is bidirectional RNNs. These guys are processing the data forwards and backwards.
So they're looking into the past and the future at the same time.
Precisely. And that lets them grab that information from both sides, past and future, which is super helpful for things like, translation.
Right, because the meaning of a word can totally change based on what comes before or after it.
Exactly. And the book, it gets into encoder-decoder architectures, which are really powerful when you need to go from one sequence to another, like with translation. So the encoder takes the input, maybe like a sentence in English, and it squishes it down into this fixed length vector. It's like a little summary of the whole sentence. And then the decoder, that takes that vector and unfolds it into the output, like the French translation.
So it's translating the meaning, not just the words themselves.
Exactly. And then to make those encoder-decoders even better, we have those attention mechanisms.
Right. We touched on those earlier, letting the model focus on, like, the key parts of that input.
Exactly. So those attention mechanisms let the decoder zoom in on those specific parts of the input when it's generating the output.
Gotcha.
It's like a spotlight highlighting the important stuff.
That seems like it would be way more accurate.
Oh, absolutely. And it gets even cooler. There's something called multi-head attention, which is like having multiple spotlights, and they can all focus on different parts.
Oh, wow.
Like a whole team of translators.
That's really neat.
Right. And then if that wasn't cool enough, there's this thing called the transformer architecture. It's kind of new, but it's been making a splash.
What's so special about transformers?
They ditched those recurrent connections from RNNs completely, and they went all in on attention.
Okay.
And they're really, really good at processing those sequences.
So it's like they took the best parts of RNNs, that attention, and just got rid of the rest.
Yeah, you could say that. They've been a game changer, for sure. Now, besides the architecture, another really important thing in deep learning is optimization.
Right, because you have to teach those models how to find the very best parameters, that sweet spot. The book goes through quite a few optimization algorithms, right?
It does. It starts with the basics, like gradient descent. Remember that one?
Right.
But then it goes into some of the more advanced ones. So things like momentum, RMS prop, Adagrad, and Atom.
It's like a whole toolkit of different optimizers you can choose from.
Exactly. And they all have pros and cons.
Okay. And picking the right one can really change how well your model trains. But the book does point out some of the challenges with optimization, too.
Like what?
So the problems that we bump into in deep learning, a lot of times they're not so straightforward.
Okay.
They can have multiple good solutions, but it's hard to know if you've got the absolute best one.
So it's like looking for the lowest point in a valley, but there could be like a hidden cave somewhere with an even lower point.
Exactly. It's a tough problem that everyone's still working on.
Right.
Now, even beyond those algorithms, the book really stresses how important computational efficiency is.
Right, because these models can get really intense to actually run, especially as they get bigger and more complex. Exactly. And so the book talks about things like vectorization, which is basically like instead of doing things one by one, you're doing them on like a whole bunch of data at the same time. Like buying in bulk at the store, it's much faster.
Right.
And that actually uses how computers work now, that parallel processing. And then there are caches. Those are like little memory banks that hold the data you need often.
So it's like having a little notepad to jot down important things. You don't have to pull out the whole encyclopedia every time.
Exactly. And all of this is super important for making sure deep learning is actually doable, especially with those giant data sets. Speaking of which, the book also talks about all the different hardware for deep learning.
Like CPUs, GPUs, and what were those other ones? TPUs.
You got it. CPUs, your workhorses, GPUs are great for all that parallel stuff. And TPUs, those are custom built for deep learning.
So it's really about choosing the right tool for the task.
Exactly. And then the book even gets into the hardcore stuff. Training models on multiple GPUs.
Oh, wow.
Yeah, it's getting more and more common, though, as those models and data sets just keep getting bigger.
Right.
And the book talks about data parallelism, where you split the data, and then model parallelism, where you split up the model itself.
So it's like having a whole team of chefs working together to bake that giant cake.
Exactly. But it's not always easy.
Right.
Trying to get all of those GPUs working together smoothly, that takes some serious coordination.
I can imagine. So we've talked about the theory, the building blocks, the tools, even some of the challenges. But what can you actually do with all of this?
Oh, the possibilities are pretty much endless. This book, it mentions a few key areas. Stuff like fine-tuning, object detection, semantic segmentation, recommender systems, just to name a few.
Okay, so let's break those down a bit. What is this fine-tuning?
Okay, imagine you've already taught your dog to fetch, like a tennis ball.
Okay.
But now you want them to grab your slippers. You're not going to start all over from scratch.
Right.
You'd use what they already know and like just tweak it a bit.
Okay.
That's fine-tuning, but in deep learning. So you take this model that's already learned a bunch, maybe it recognizes objects and images, and then you adapt it for something new, but it's a related task.
So it's like transferring skills from one thing to something else.
Exactly. It saves so much time and effort compared to starting from zero. And then object detection, that one's pretty straightforward. It's finding the objects in an image.
Like circling all the cats and dogs in a photo.
Exactly. And that has a ton of uses. Self-driving cars, robotics, even in medicine.
That's incredible. What about semantic segmentation? What's that one do?
So that one takes object detection even further. Instead of just putting a box around it, it actually labels every single pixel in the image.
Wow. So it can tell you which pixels are the cat, which ones are the dog, all of that.
Exactly. Like a coloring book, but with pixels. And that is really important for self-driving cars where knowing what's in the scene with that level of detail, it's crucial.
And last but not least, recommender systems. Those are everywhere these days.
They are. Think Netflix, Amazon, you name it. They're using those recommender systems to figure out what you might want to watch, buy, listen to based on what you've done before, what you like.
It's both amazing and slightly creepy how well they know my taste sometimes.
Right. It's all thanks to deep learning. They're analyzing mountains of data on your behavior and preferences to make your experience, like, super personalized.
Wow. This has been an incredible deep dive. I feel like I've learned so much about what deep learning can do.
It's seriously powerful stuff. And this book, Dive into Deep Learning, it's an awesome place to start for anyone who really wants to get into this.
It really is. I mean, we've just scratched the surface here, but we've gone over so much. The basic ideas, how it works in practice, even some of the challenges and what the future holds.
And, it also brings up something really important about deep learning. It's not just about building those cool, powerful models. It's about making sure we're using them the right way. As all of this technology keeps getting more advanced, it's woven into our lives more and more, it's super important to think about the ethics of it all, to make sure that those systems are fair, unbiased, that they're actually helping everyone.
That's a really important point. This technology has the potential to, really change the world, but we need to make sure that we're steering it in the right direction.
I completely agree. And that's something that we all play a part in.
Well said. This has been an awesome journey into the world of deep learning. I've learned a ton.
Yeah.
Thanks so much for joining us on this deep dive.
It was my pleasure.
And to all of you listening, we hope this sparked your curiosity and that you'll keep exploring this incredible world of deep learning. Dive into deep learning. It's a great starting point. Keep learning, keep experimenting, and never be afraid to ask those questions. The power to shape the future of AI, it's in your hands.